Can you hear me well? The sound is okay. Great. Hello everyone. Thanks to the organizers. So this is a very nice meeting. I recall previous editions in Paris. But this is a good enough substitute for this time. So today I'll tell you about what we call influence matrix approach to many-body dynamics. And you will see that temporal entanglement that I would introduce plays a key role in this approach. I will discuss several applications ranging from thermalizing system to many-body localization. And it's based on a series of papers that we wrote over last year with Alessio Le Rosa and Michael Sonner here in Geneva. And please do not hesitate to interrupt me if something is unclear. These days we are witnessing really a lot of progress in experiments with synthetic quantum systems, such as ultra-cold atoms, right, which are really kind of designer quantum systems. They're very tunable. You can change things like dimensionality, interactions, and in many ways, they're very much unlike conventional materials. So they're isolated, they have no phonon or other heat path, and they have very long time scales. And that makes them very good platforms to study non-equilibrium quantum physics. The systems also naturally allow you to do different kinds of experiments. So one that has been already discussed, I guess, yesterday is a quantum quench. So you can just initiate your quantum many-body system in some initial state and then let the degrees of freedom interact and see what happens. And also realize new setups such as coherently, periodically driven interacting systems. So these are kinds of things that people are interested in. And theoretically, sort of a general theme over the past several years has been aiming to understand different, let's say, universality classes of non-equilibrium dynamics, right? So can we have, in some sense, a similar notion to a phase of matter in equilibrium, right? So what are different kinds of dynamics that you can find in physical systems? This line of research, it's also connected with the efforts to find new efficient ways of controlling synthetic systems. So that's something that Alex mentioned at the end of his talk. And so what do we know now about different kinds of dynamics in isolated systems? So that if you consider a closed system, by far the most common possibility is that you would thermalize. So you would forget initial state and fall to a state that looks thermal. And in that case, we say that our system can act as a good thermal bath. A second possibility is many-body localization. So in that case, because of disorder, your system preserves the memory of initial state, and in some sense, quantum coherence is locally protected because you have a lot of local integrals of motion, and in that case, you say that the system is a bad path. There are also other possibilities, right, which are being actively explored, which I group here under the name weak ergodicity breaking, and this includes things like quantum many-body scars and fracturing of the Hilbert space and so on. And there are also things like pre-thermalization that that are mechanisms to slow down your thermalization for this can happen in various ways. So how do we describe quantum many-body dynamics? There are a few common ways of thinking about it. So what you would like to do, let's say you would like to describe unitary evolution of some initial many-body state psi 0, and usually you try to understand either the structure of the eigenstates, so you can try to do it perturbatively, like for the case of many-body localization. In some models, you can do it exactly. Or there are also general powerful ideas like eigenstate thermalization hypothesis, which tell you what are the properties of eigenstates, for example, in thermalizing systems. Numerically, you're quite limited. Essentially, you have to live with exact diagonalization. Another approach is to really try to track the real-time evolution of your system. And this you can do numerically in various ways, also exact diagonalization, a variety of tensor network approaches, which rely on the entanglement of your many-body wave function staying low for at least some time of the evolution. So this is the usual toolbox that people have been using. But at the same time, based on these measures, we usually try to determine whether a system is a good bath or a bad bath. And so what I want to do today is take it a little bit more literally, right? And really try to describe a many-body system as a quantum bath. And so, to that end, we would go back to classic ideas about simple quantum systems coupled to a bath by Feynman and Vernon. And so let me start with talking about this approach to thermalization. And so this will resonate with talks by Tomasz and John yesterday. So one way of thinking about a quantum system coupled to a bath was proposed by Feynman and Vernon. This goes under the name of influence functional. So the idea is the following. So let's say we have some simple quantum systems such as a spin described by coordinate q of t, and it's coupled to a bath, which I'm going to describe by coordinates q capital of t. Then what you can do, you can write the time evolution of this combined system using Keldysh path integral. And so you would have two copies of your evolution for forward and backward contour. And then so you can, at least formally, you can integrate out the bath degrees of freedom. And what you would end up with would be a path integral just for your system, which would include the action of the system. But it would also have an additional piece which describes the influence of the bath. And that's the influence functional. Right, so I wrote it here, so it would depend on the action of the bath and action which describes interaction of bath and the system. So here you see, Cyrillic subscripts because I copied it from a Feynman-Hibbs book on path integrals. And this generally gives you a non-local action for the system only. And it acts on forward and backward trajectories. So that's the idea. This had been very, very fruitfully used, in particular in describing dynamics of the dissipative two-state system. As a model of the bath, typically one chooses a bunch of non-interacting oscillators, because then you can carry out this integration explicitly and get the explicit form of the influence functional. And that's exactly the starting point of this work by Leggett and collaborators, right? So it's a long review paper describing different regimes. So this is a very rich and interesting problem. But what we want to do today is to move away from this model of a bath as harmonic oscillators, and really, so we'll try to view a many-body system as a bath, and we would be thinking about the influence functional of a many-body system. Just before I dive into the results, so just a small piece of intuition about the influence functional. So let's say we consider a quantum spin subject to interaction with an environment, and it in the Keldysh formalism, so we consider forward and backward trajectories, sigma of tau and sigma bar of t, and classical trajectories are the ones where forward and backward trajectories are exactly the same, right? So sigma is equal to sigma bar. And quantum trajectories are the ones where sigma and sigma bar are different, at least in the part of the trajectory. And those describe really quantum mechanical interference contributions. And as a simple, simplest possible model of environment, let me choose classical noise, classically fluctuating field in the z direction. So this field has some correlator, f of t minus t bar. And in that case, your influence functional would be quadratic, right? And it would look like shown here. So here, yeah, somehow I don't have a way of pointing, but okay, yeah, I hope you can follow. So and what you see here is that if sigma is equal to sigma bar, you don't pay anything, and influence functional is 1. But if they're different, there is a suppression, right? Then essentially the idea is that when bath measures you in some sense, right, could be classical bath or a quantum bath, this suppresses interference contributions, right? So that's the physics we are after. Let me start with Floquet model. So this is sort of a Drosophila fly model of Floquet dynamics. So it's a kicked Ising model, non-integrable. So kick would include rotation around x-axis followed by rotation around z-axis, and then there would be a z-z interaction. Sorry, I see there is a chat on this question. There's a question: G is a Green's function in the previous slide. Yeah, for the noise in that case, yeah. And right, and the idea of what we're gonna do is essentially, in this case, we cannot integrate out the bath of spins directly, but what we're gonna do, we would consider, let's say, left part of the chain as a bath, and then if our system is translationally invariant, a spin evolving under the influence of this bath should look like the same kind of bath to its right neighbor, right? So there is a type of self-consistency equation for the influence functional, and that would be the starting point of our approach. So this has a very simple representation in terms of tensor networks. So in this case, we can introduce this notations shown here for all the gates. So here I have a kick, which is a blue square. I have an interaction, right? Interaction, which is the red oval, and the z field is this green tensor here. And when we're thinking about the real-time evolution, so this is represented as a Keldysh path integral, right? So this tensor network would have a forward and backward copy, as also appeared in the talks yesterday. What we will do, right? We will contract the network in the space direction, and this idea has been explored first in the tensor network community by Marie-Carmen Banous and collaborators about 10 years ago, this means, right, that integrating out environment amounts to taking a high power of this dual transfer matrix, which I sketched here. And its eigenvector with eigenvalue 1 is exactly the influence functional. Or since we are dealing with discrete dynamics here, we call it influence matrix, right? So you can view this eigenvalue equation for the dual transfer matrix as a self-consistency equation for your influence for the influence matrix of your system, right? And here, again, let me remind that the dual transfer matrix has a forward and backward part, right? So all the gates are doubled. So, and as discussed yesterday by Tomasz and by John, right, this idea of transverse contraction of a tensor network and idea of space-time duality has been extremely fruitful, right? So in particular in the context of dual unitary circuits, but also in the context of what Vedika was talking about, so non-unitary circuits. So and now, so where how can we make progress from the self-consistency equation? Well, so let us first ask, so what is the simplest possible form of a thermalizing influence matrix in a Floquet system? Well, we can imagine a system which acts as a very strong bath, right, which essentially suppresses exactly all the quantum trajectories, right? So it forces you to forces the forward trajectory and the backward trajectory to be the same, right? So we call this a perfect dephaser, right? And this really corresponds to a Markovian behavior of your bath. And remarkably, it turns out that there are various models which actually behave in that way. For the quantizing model, this happens at the dual unitary point when epsilon is equal to j. So epsilon was a parameter of the rotation around x-axis, and j is the z interaction. So when they're both equal to pi over 4, this corresponds to this very simple form of the influence matrix, right? So of course, this has been the fact that these models are, in some sense, solvable has been discovered, right, by using this dual unitarity property, right? So, but this gives us a flavor of how this approach could be useful. So there are cases where, despite the fact that you're dealing with a complicated many-body system, right, influence matrix is very, very simple and can be found exactly. So now, right, you see that this perfect dephaser points are quite special. If I view now the influence matrix as a wave function in the time domain, right? So I will be thinking about the sort of temporal spin chain, right? Where at each moment of time, I am thinking about spin on the forward contour and on the backward contour. So my Hilbert space is doubled, right? So I'm going to view this whole trajectory as a spin chain, and often it's useful to think of the influence matrix as a wave function, fictitious wave function on that chain, right? And what you see is that at such solvable points, this is just a product state, right? So, but that means that it has very low temporal entanglement, right? So by temporal entanglement, I mean exactly viewing influence functional as a wave function and then cutting it somewhere along my evolution. And what this also tells us that as we detune from such solvable points, things should remain relatively simple, right? Because entanglement should be continuous, and this relatively low amount of entanglement in the vicinity of perfect dephaser points should stay. And indeed, so we have checked that this is the case, right? So and here is an example of showing what happens as you detune from this perfect dephaser or dual unitary point in the quantizing model, right? So you see that entanglement grows, but its slope vanishes at the perfect dephaser points, right? And here you see a plot in the instant of the slope, right? So what this tells you that this way of thinking can be much more efficient than thinking about let's say, relying on the low entanglement of your real space wave function. So more generally, what is the structure of the influence matrix in the ergodic phase? Right. So at the solvable point, it's extremely simple. You just suppress all the quantum trajectories. More generally, so you can view your trajectory as a collection of classical parts, right, and bleeps and sojourns, where and bleeps where forward and backward spins are actually different, right? So here you see an illustration of that. So pink regions are bleeps, and then other regions are sojourns. And what you find is that this gas of bleeps has very quickly decaying interactions between them, right? So here you see several examples at non-integrable points, right? And you can see that the interactions between the bleeps quickly decay with the distance. And so, and based on that, and also inspired by some of the approximation developed by Leggett in the context of dissipative two-level system, you can, for example, realize that for describing an impurity coupled to this many-body spin bath, non-interacting bleep approximation can be very efficient, and that allows you to, for example, predict how quickly magnetization of this impurity would decay. Right, so that's just to give you a flavor of the kinds of analytical calculations you can do in this approach. And so let me jump to part 2. Of course, if there are any questions, please don't hesitate to ask. Okay, so then I continue. And so second, let me talk about continue the discussion of temporal entanglement, and I will show that in systems with quasi-particles which are integrable, with non-interacting quasi-particles that are integrable, temporal entanglement actually follows area law. So as I already mentioned, if temporal entanglement of the influence matrix is low, that allows us to find new solutions and efficient MPS representations. So therefore, in this approach, the key question is, when is temporal entanglement low? And so I gave you the first example, which is near perfect dephasor point. So there we can show that that it must remain low for at least a long time, right? And more generally, you expect intuitively that in a system that is quickly thermalizing, influence matrix would have quickly decaying correlations and likely low entanglement. And in this part 2, so let me describe it to you another example of a free fermion bath. In this case, we can show analytically that temporal entanglement follows area law. And in the third part, I will show that even a very different kind of systems, non-ergodic systems can also have low temporal entanglement. And this second part has implications for open quantum systems. So in particular, there are very interesting attempts to use tensor network formalism to describe non-interacting bath, and this result that I will present shows that this is fruitful, right? This is guaranteed to be efficient. And as a solvable model, we choose again the same Kick-Tizing model, so it's extremely rich, actually, despite its simplicity. And what you need to do is just turn off the Z field H, and then you end up with a model that maps onto free fermions. So this Floquet model has quasi-energy spectrum of quasi-particles, which is written here, right? So these are quasi-energies you have, and with some work, you can integrate out the environment. And so in here, it's important that environment is initialized in an infinite temperature state. And what you find is that in that case, influence functional has a form, so it looks like a BCS type wave function in this time domain, right? So here is an explicit expression here, and the key part is the pairing term, right, which is written here. So it's this function kappa that is related to the properties of quasi-particles. So you see phi k popping up here, and also you see this coefficient ck. So that tells you how a fermion operator at the boundary is related to quasi-particle operators, right? Because of course in this approach, you are thinking about half chain acting as a bus for for a chosen spin. So, but effectively, so this gives you an expression for the spectral density of your bath, not relying on the smallness of coupling, right? So this is an exact answer. And so generic feature that you find here is that the spectral density kappa decays as a power law as 1/tau to power 3/2. So there is fictitious pairing in your temporal spin chain, but it decays relatively fast. And this can be understood as stemming from the Van Hoff singularities in your quasi-particle band structure. And the fact that now you can view influence matrix wave function as a ground state of a fictitious quasi-local Hamiltonian, right? And therefore it must satisfy area law. And that we have confirmed numerically. So here you see, right, you see the scaling of this entanglement, temporal entanglement for different evolution times, right? At different choices of parameters. And in the inset, you see that you see how spectral density decays, right? So you can do more with this approach. So here, for example, if you look at the saturated value of temporal entanglement at long times, which is shown here on this plot as a function of your field and ZZ interaction, that reveals the phase diagram, right? So you see that the diagonals are exactly where the phase transition happen, and you can get edge modes in this model, right? So temporal entanglement jumps across these phase transition lines, and interestingly, also here at the crossing, so in the center of the square, spectrum of your quasi-particles becomes linear, and that's exactly the dual unitary or perfect dephasor point. And what this tells us is, in particular, is that the fact that this integrable system has area law temporal entanglement, it tells you that influence matrix provides an efficient description of weak integrability breaking, right? So when we add let's say weak interaction or something like that, it is guaranteed that matrix product states method would still be efficient. And we've done such simulation, so I'm not going to show them today, but feel free to either ask me or look it up in the paper that I mentioned. And with that, so let me jump to the third part of the talk, which is influence matrix approach to many-body localization. And so, this will have this has certain connections with what John was talking about, although they consider spectral form factor, while we are interested in the correlation functions, right? So our transfer matrix is different from theirs. So the general idea of MBL is that when you crank up disorder and your interactions are short range, your system fails to thermalize. And the model I will concentrate on today is again the same model, where now I would make Z field disordered on different sides, and G and J should be sufficiently small for MBL to be possible. So when system enters MBL phase, it is a bad bath, right? It has that manifests itself in a number of properties. So eigenstates have only area law entanglement, and memory is preserved, which means that if you look at the correlation function magnetization on a single side, it would stay finite even as time becomes very long. While in a thermalizing phase, you forget, right? You forget initial state and this decays to zero. And that's exactly what we would capture. We would capture with the influence matrix approach. And we just saw that in a thermalizing phase, influence matrix, its structure, you can think of it as a weakly interacting guess of blips, right? So blips cost you certain energy, right? And they their interactions fall off. But what is the influence matrix of a non-ergodic system? Right, so we'll try to get some insight into this question. The way we're going to do it, in this approach, you can carry out disorder averaging from the outset. And what this would do in the path integral formalism, it would give you, right, it would give you the average of a phase e to the IHJ times difference of the forward and backward trajectory. So if we choose Hj to be uniformly distributed from 0 to 2 pi, then averaging this term, we would just get a delta function, which forces the magnetization on the forward and backward contour to be the same. And so, and this has been previously used by Bertini, Kos, and Prozan in their work on dual unitary circuits, this way of disorder averaging. And then, you know, very convenient thing about this approach is that you can just now study the self-consistency equation for the disorder averaged influence matrix, right? So pictorially, what I'm adding here is a non-local constraint. So here, you know, denoted by this green tensor, which effectively projects onto the sector where magnetization is the same between forward and backward contours. And what is nice is that in principle, all the rare regions effects are accounted for, right? Of course, now your goal is to understand the properties of this eigenvector of the disorder averaged transfer matrix. So phase diagram looks as I described. So if G and J are sufficiently small, your MBL, if they're larger than the threshold, which in this case is at about 0.4, you go to a thermalizing phase. And you know, so we've implemented the MPS algorithm to find the solution for the eigenvector of the disorder averaged transfer matrix. And what you find is that in the MBL phase, growth of the temporal entanglement is very slow. So it's strongly sublinear. So you see it on this plot, right? It appears that entanglement saturates, entanglement entropy saturates as a function of time. And this is in contrast to the ergodic phase where, and especially the transition where entanglement grows faster, right? Seems to grow linearly, at least at short times. And an important remark. So here, you know, I'm always talking about so-called folded transfer matrix. So I consider forward and backward configuration at the same time as being one side of my temporal spin chain. But you can also unfold it and then ask what is the entanglement between, let's say, forward and backward contour. In the case of MBL, it also remains low, while in the ergodic phase, actually, it is typically very high. And as I mentioned, so this allows you to get, in principle, all temporal correlators once you know influence matrix. So here, actually, maybe I went a bit too fast, but the idea is that if you have the influence matrix, then to find some temporal correlators, you just need to contract contract the evolution of your single spin with the influence matrix and insert at appropriate times the operators you want to measure. So if we want, for example, the ZZ correlator Z of T, Z of 0, I have to look at the network shown here and insert, right? I would insert Z operators at time 0 and at time T. And this gives you, this picture for monetization evolution. So you see that that it saturates, right? It saturates when disorder is strong, so that suggests MBL, and then it decays. It decays when disorder gets effectively weaker. And this really, because the temporal entanglement is low, this gives access to long-time dynamics in the MBL phase, right? With this nice feature that you're already computing disorder averaged quantities, right? So you don't have to worry about disorder averaging as you usually do in these kinds of problems. And so, here I'm showing it up to time about 30, so one can push to really much longer times because temporal entanglement remains low. And maybe in the last, so I'm almost done, so I'm about to stop. So just the last remark. So regarding the structure of the non-ergodic influence matrix, right? So there are really some very dramatic differences compared to the familiar influence matrix of a thermalizing system. So in this case, the blip interactions are non-local and they do not decay, which physically exactly reflects the fact that interference remains important. It persists in this system because effectively your local, your local spectrum is discrete, right? So your bath cannot kill interference, and effectively what this also means is that if I think about the weight importance of different sectors, different monetization sectors of the influence matrix, turns out that in the non-ergodic phase, it is monetization sectors with large monetization that dominate. And so, and let me again finish with this note that actually Sam Garrett and John, they consider the different dual transfer matrix, but it would be interesting to sort of make a bridge between the two ways of thinking about it. So I stop here. So in the future, so really there are many interesting extensions. So we're planning to look at open systems with this. So it's very easy to add external dissipation, transport, and various other things. And so thanks a lot to the collaborators, and thanks for your attention.
Thank you. Thank you, Dima, for the very nice talk. We have time for questions. Please mute yourself or write in the chat. Not in the meantime, I will start the question. So Dima, going back to the very basic idea, I was wondering, I guess in general for a many body system, the construction of this influence functional, I guess you can do it, but it will not have a simple form, like, for example, in the Feynman-Vernon. Can you say something more about what allows you to actually trace out do this part of the system? I guess this is somehow hidden in the in what you call the self-consistency condition. What that means. And maybe, I don't know if you can make, for example, there are situations in which this kind of ideas, for example, dynamical midfield theories are formalized, but in that case, you use a large connectivity limit to do this calculation, right? Here you are doing in 1D. So can you elaborate a little bit on this point?
Yeah, no, that's an excellent question. So I think again, right, there are sort of controllable limits, and these are, to us, first of all, fast thermalization, because in that case, you know that your dynamics should be, it should forget, right? It should forget, it should have a short memory time, right? And therefore you're expecting that, you know, effectively in the language of influence matrix, that corresponds to fast decay of interactions between blips, right? And, you know, these perfect dephasers are just an example where yeah, essentially this intuition is just exact, right? And the interaction range is 0. Now, we don't yet know whether for thermalizing dynamics, you must satisfy area law. It could be, right? But it's clear that it's only structure of the influence functional over this memory time that should matter, right? So I think, I don't know, yeah, I hope that answers at least partially a question. Yeah. Now, for MBL, it's a different mechanism, right? For MBL, it's rather because information spreads very slowly. So effectively your bath that you are feeling remains low, right? And that's why, you know, temporal entanglement is low in both cases, but really the structure is completely different. Mm-hmm. Right, but honestly, I think this is very much open for
yeah, so Jared, I see there is another question, and I'll get to yes in a second. Just to follow up, so in one example, you have this area law temporal entanglement. So can I understand this? So you show this memory kernel that decays as a power law, but kind of a large exponent, you would say. Can I draw a connection with a sort of Leggett-like delocalization? So if I look at the spectral function in frequency, can I say that the bath is somehow as low enough spectral weight that the system thermalizes? Yes. The system doesn't spread entanglement?
I think you probably can.
I think you have a slide in which you show that this kappa of T, yeah, exactly, this guy.
Right. Yeah. So this is generic for this kind of, you know, infinite temperature system with quasi-particles, this decay of 1 over tau to power 3/2. Now, what we are considering now is, for example, if you have a Fermi C bath, right? So low temperature, then I think things like you're describing will probably happen, right? But here maybe just a really short thing. So another example of when temporal entanglement is low and this is efficient, you see here, right? Because your quasi-particles are non-interacting, so it's a quadratic wave function. But the expectation is that in a generic thermalizing system, you know, you'd have some 4-particle interactions and so on, but it's only local, right? That's the hope, with some controlled corners where we know it's like that.
I see. So please, Jesko, you can unmute yourself and ask the question if you want.
Hi, yeah, I have a question about the last part of your talk about this exact disorder averaging. And just to understand that better, I was wondering, is there a connection, say, if you have a system with a discrete disorder, there is also this idea to use sort of ancillary spins and sort of purification, and then you get the exact disorder average. I mean, I understand here that the copy is sort of different, but can I understand it in a similar way, why the exact disorder averaging works here in this case?
So I'm guessing you have in mind this papers again by Mari Carmen and Sirac, right, where you take discrete disorder, so you can just effectively, you have a translation invariant chain. Usually they work in real space, right? So here we are doing it in the in the temporal domain, so that's a bit different, I would say.
Right. But you know, I understand that this is in the temporal domain, but I was just wondering, I mean, the reason why at the end sort of the exact disorder average is sort of realized, if it's sort of, if one can think about it in a similar way as sort of some spin and ancilla spins, and if you sort of at the end you have some effective tracing out? So I just try to understand better why you have the exact disorder average here.
I think this is just in this approach, this is very simple, you know, in the same way as also averaging over ensemble here is very simple, right? Right, that's another, I mean, another nice feature of this approach. You can average over different initial states, different realizations of your model, right? Yeah, it's just how this construct. Of course, you know, there is no free lunch. This constraint is non-local. So, and practically this means that the bond dimension of this green operator here is large, but still, you know, it's manageable. It's not crazy large, so you can still have efficient algorithms.
Okay, thank you.
So thanks for the question.
So last question by Philip that I see.
Hello, Dima. I had a quick question, sort of similar to what Marco was asking, which is sort of you had a special case of the dual unitary point where entanglement was, except for this tempo entanglement, was still very small. Do you have cases where this tempo entanglement grows very quickly? What's the opposite extreme? Is it something that's just generically thermalizing, or is there something different?
Yeah, that's an excellent question. So I think when indeed, you know, in this model, there are some corners where it grows faster. I wouldn't say there is a case where it's really sort of shooting up through the roof, right? In general, again, so this intuition, well, let me give a disclaimer that really, I think not much is known at this point about general properties of temporal entanglement, but our intuition is that if your system, let's say, is showing some oscillations, thermalizing slowly, right? There is long thermalization timescale. That's where it would stay high, temporal entanglement. I would say, I don't know. So Alessio is in the audience. I don't know if he wants to add to that.
So something where you do thermalize, but the time scale is very slow, or you sort of have some glassy relaxation dynamics. You expect this to be large.
Yeah, let's say, or when you have several time scales, right, for different quantities. Another thing, you know, we are looking at and should have results soon is systems with conserved quantities. Well, in a sense, okay, in a sense, this integrable model has conserved quantities also, right? But maybe, let's say, if you have diffusion, it would be interesting to see what it means for entanglement. Right, and we should have results on that soon.
Great, thanks.
Yeah, thanks.
Okay, so I see there is another question, but I think we should maybe thank him again, close this section. I will leave the Zoom call on.
Yeah, I'll stay here in case.
You can stick around. We will reconvene here at, as the schedule says, at 4 p.m.